Hello everyone. In this video, I'm going to explain to you standard solutions and especially the equipment that we use for measuring standard solutions and why they're so important. We won't look as much at dilutions, but as part of this dot point, you do a dilution as well. So first of all, what are standard solutions? They're solutions with an accurately and precisely known concentration, and I mean very accurately, very precisely, like 4 or 5 significant figures. A primary standard is made by dissolving a solid. So we take a very carefully known, very carefully measured amount of the solid, make it up to a very accurately known volume. We get a primary standard. A secondary standard is made by diluting a primary standard solution, or by taking another solution and using your primary solution to work out what the concentration of the other solution is. But they're all standard solutions. We know the concentration very accurately. Why are they important? They are very important in analytical chemistry for determining unknown concentrations. That's what we're often doing. I have an unknown, which could be in industry, some sort of medicine, a chemical, a food product, and we use the very accurately known standard solution to work out and determine the concentration of the unknown or the amount of the unknown. Very important. What are the requirements? You can't just take any substance and use it to make a primary standard solution. So these are some of the requirements. It's got to be soluble. That's obvious because we're going to prepare a solution. You want a large molar mass. If it had a molar mass of, say, 5 grams per litre, then when we prepare a 1 mole per litre solution, we put 5 grams in. 5 grams is quite small, and even small errors in your weighing become a large percentage error. Whereas if you use something with 150 molar mass, 150 grams per mole, then when we make a 1 mole per litre solution, we need to put 150 grams in. And that means a small error in your weighing becomes a much lower percentage. So large molar mass. Pure, obviously. We want something that's hydrophobic. It doesn't absorb water from air. Lots of chemicals do absorb water from air. So we want a hydrophobic chemical, and often we'll store it in a desiccator to make sure it's really dry. And the last one, something that's stable in the presence of air, because many substances react with oxygen. Now, you don't need to memorize those requirements for a good primary standard, but we will use those in Year 12, and you will need to know them in Year 12. So that's what a primary standard solution is. How do we prepare it? We need to use volumetric glassware, and this measures volumes very accurately. It's used in volumetric analysis. That's a term you'll start to hear more, which is when we measure amounts of substances very accurately based on volumes. You might have come across gravimetric analysis, where it's based on mass, but often we're doing volumetric analysis. So what sort of glassware? We do not use these things in volumetric glassware. Beakers. You should not have been using beakers for measuring, even in Year 7 to 10 science. They are nowhere near accurate enough. They are just for holding solutions, storage, not long-term storage. But also, so not beakers, measuring cylinders. That's what you would have used in junior science to measure things. You do not use measuring cylinders for measuring in volumetric analysis. They are nowhere near accurate enough. To give you some idea, measuring cylinders are only accurate to within 5%. So if you measure 10 mils, really what you've got is somewhere between 9.5 and 10.5 mils. And you may think, no, I'm more accurate than that. I get right on the 10. Well, it's to do with how well that measuring cylinder is made. When they make it mass produced, they put 10 mils, but you put exactly to that mark, you don't necessarily have 10 mils because there's errors just in the way the measuring cylinder is made. Volumetric glassware, very carefully made, very accurately calibrated, so to within 0.2% to 0.5%. We're talking a huge difference, like the errors are 10 times smaller or even smaller than that. So what are the 3 bits of volumetric glassware you'll be using? You need to learn these 3 and their uses in Year 11, and then you'll use them in Year 12. First one is a pipette. These are for delivering a fixed volume of liquid. I've underlined those 2 words, deliver. So it's not for storing or for a reaction, just for transferring the volume into a different container. And it's a fixed volume, meaning each pipette has a certain amount that you can transfer with it and you can't change that. So common volumes are 5, 10, 15. You can see in the pictures here, they've got the numbers written on them, 25, 50, 100. There's also a lot of other writing. Often they'll tell you which standards they meet, the percentage errors or the error in mils, because that's important in volumetric analysis. That's why there's so much writing. So the pipette is the first one. There are graduated pipettes that have scales on the side, but we won't use those as much. So pipette, first one. Second one, a burette. This is much bigger. You can't tell from the picture, but they are about 1 meter long. When you put them in a clamp, it's hard to reach up into the top to pour things in. And these deliver a variable volume of liquid, still delivering. So you don't do your reaction in a burette. It's just for transferring a liquid, measuring a certain amount into another container, but it's a variable amount. You can see in the picture probably there's a scale and there's a tap. Sometimes we call it a stopcock. It's a tap at the bottom, and you can turn that tap and control very precisely and carefully how much liquid is coming out. You can go drop at a time if you want to. So it can go faster, but it can go drop at a time, and you can measure a very exact amount of a liquid into a reaction vessel or something. So that's the second one. The third one, a volumetric flask. These are used to contain a fixed volume of liquid. So you're actually making up a solution that you are then going to keep and be using in your investigation. So not just for transferring, you're containing it, and it's a fixed volume as well. You can see this one is 100 mils, and it's got a line there on the neck. That's really important. The way we would normally prepare the solution, you put the solid into the volumetric flask, or you put a certain amount of another solution into the volumetric flask. You could use a pipette for that. That's normal. And then once you've got it in there, you add your solvent, like water, all the way up to that line. And when you've got your meniscus just at the bottom of the line, you know you've got the 100 mils. You'll also notice with these, the shape. So let's go back to the pipette. You've got a big bulb in the middle, a long skinny bit at the bottom and the top. That's because if you have a very narrow tube, the liquid moves up and down much quicker when you change the volume. And so when you're getting it to a mark, you want it to be in a skinny tube, so you're really getting it very accurate. If it was in a big brown thing, you can't tell exactly how much is in there. It goes up and down very slowly as you add more. So these pipettes, they have a line on them as well. You can maybe just see one there, and it's on the narrow bit where the liquid is moving very quickly as you add it or take it out. And it's the same with the volumetric flask. The neck is much narrower, and that improves the accuracy. So they're the 3 bits of volumetric glassware, and in the activity, you will fill in a table. Try to do it without looking. So go over these. There's a document that has information on them, but then try to summarize, state the 3 names, state their purposes without having to look. The last thing, what are the calculations involved with primary standards? Well, you've already done these, just not in this context. Let's say we want to prepare a standard solution of a particular concentration. So we know the concentration we want, and we've got our volumetric flask, so we know the volume. Well, you know concentration and volume, so you can work out the number of moles that you've got to put in there, concentration times volume. So you work out the number of moles you need. And then, if you know the number of moles, you can easily work out what mass that is. Using number of moles is mass over molar mass, but we rearrange it. So if you want to make, say, 500 mils of 0.5 mole per litre solution, you can work out what mass to add. What about if you've measured a mass? Because it's actually very hard. Let's say we work that out and find we need 47.2634 grams. It's hard to measure that. So what will often happen is you prepared your primary standard, but you couldn't get your mass exactly right. So I know the mass I've got. What's the concentration of the solution I ended up with? Well, you can do that, because if you know the mass, you can work out how many moles you put in there. Number of moles is mass over molar mass. Once you know the number of moles, you can work out the concentration, because you know concentration is number of moles per volume. And what do you notice here? These 2 formulas that we've learned, number of moles is mass over molar mass, concentration is number of moles divided by volume. They are really important. So make sure you're used to using them, laying your calculations out properly, put in units, and they're both on the formula sheet. So you'll use them a lot. So in this lesson, you're going to see if you can summarize those 3 bits of equipment into a table. You'll practice a few calculations for primary standards. And when we're back in the lab, probably in week 3, we'll get you to prepare a primary standard in the lab, and then to dilute that primary standard to get other sort of standard concentration solutions.